Okay, so today we're going to talk about convex optimization. So previously we talked about empirical risk minimization, which when the losses are convex is going to be able to be cast as a convex optimization. This will help us understand why things like gradient descent and stochastic gradient descent work, how to think about subgradients, which we'll actually go through in this lecture. And this is really not a complete picture of convex optimization. It's just pretty much the things you need to know to understand stochastic optimization, the origins of stochastic optimization from the convex perspective. And typically we deal with the convex perspective, not because we think everything has to be convex, but because it's very instructive to think about convex optimization as a first test case for thinking about stochastic optimization in general, because subgradients make sense in that context. So, if you want, you can read the first chapter of Boyd and Vandenberg. You could read the first 4 chapters of Boyd and Vandenberg if you want. You wouldn't see all of this material in there. This is sort of a hodgepodge of material, but it's really, I stripped it down to the bare bones of what you need to know to understand stochastic optimization in this context. Okay, so before we talked about training and test sets, and before we get to convex optimization, I just wanted to talk briefly about cross-validation, because we didn't quite get to that last time, and it really is something we should talk about a little bit because it doesn't take too much. So before we did training and test splits, right? And sometimes we are splitting our training set further into training and validation, and this holds for either case, right? It's pretty much just when you want to be able to evaluate your risk after you've trained, then you need to have either a test set or a validation set if you're further splitting your training set into training and validation. So we're just going to talk about it as training and test sets, but remember that this could be a validation set if you've already done a training test split. So when you do this training test split, it seems a little sloppy, right? You hold out 2/3 for the training set and 1/3 for the test set, and then you lose a lot of the data in training if you make this test set large, but if you make it too small, the test set too small, then you won't have a decent estimate of your true risk, right? So what we do is if this test set is small, then what we use cross-validation to sort of stabilize this test error. And the way that we do that is we will just think about repeating this process of holding out, doing a training test split, holding out a test set from our training set, and refitting on the training set and reevaluating on the new test set, right? So to stabilize this test error, we just are going to continually do this process multiple times and then average the resulting test errors. And this is called cross-validation. So there's a lot of ways in which this can happen, but the most common way is KFold cross-validation. So in KFold cross-validation, we partition our data into K sets of size n over K, and we do this randomly. So we just group the data into these K sets of about equal size. And then for each of these sets, we fit on all but the ith set. So we say we're doing 5-fold cross-validation. We have 4 that we hold out that we set aside for training, and 1 that we set aside for test, right? And we fit on that 4 out of the 5 for training, but then we test on that 5th. Now we rotate what our test set is. So we start with the first chunk being the test set, then the second chunk being the test set, then the 3rd chunk, 4th chunk, 5th chunk, and then at the end we get this test error, we average it at the end. Leave one out cross-validation kind of takes this to an extreme, where we set K equal to N. So the way to think about that is every sample is its own holdout. So we hold out the first sample, the first data point, make that its test set. So the error is just a loss over that test point, right? And then we continually do that, and we average all n of those. And that's pretty extreme because now you have to do the training step n times. So it multiplies your training computational complexity by a factor of n, right? And so this is a pretty extreme way to do things, but sometimes we're lucky and we can do this leave one out cross-validation effectively for free. And we'll talk about those sort of situations. So let's go back to the main topic, convex optimization. So convexity, let's just define convexity first. A convex function is a function, and typically we're thinking of this as a function mapping the feature space, which is p-dimensional, into, or label space, which is R, right? It's just one-dimensional in some cases, but this can be generalized to multi-dimensional cases. A function is convex if for any alpha between 0 and 1 and 2 points, we have that f of this convex combination of x0 and x1, these are the 2 points in Rp, this convex combination is bounded by the convex combination, the same convex combination of the function values. The picture here really says it all. So you have this function f, and then when you say that we're going to create this line effectively, which is parameterized by alpha, so when alpha is 1, then this evaluates to fx naught here, right? And when when alpha is 0, it evaluates to f at x1 here, right? So we're just drawing this secant line, and we're just expressing what the secant line is, and we're talking about the interior of the secant line here, right? And if it lies above this function here, and this holds regardless of where we set this x0 and x1, then we say that the function is convex. So basically the idea is that the function has to lie below the secant line. So a lot of you probably know what convexity means, but I just wanted to review it. And you know, all the time I'm forgetting the directionality of this inequality because I'm not that smart, and so all the time I just think of this picture, right? So definitely don't be ashamed if you have to think of the pictures to remember the directionality of these inequalities. Right? So convex optimization, the basic idea is that it's just a certain type of optimization, which is really an idealized statement of a procedure, right? An idealized procedure or an algorithm which minimizes, so that means it finds the x and the value of f that minimizes f of x, where if f is convex, then this is a convex objective. Right? Now, this could be subject to constraints. So, you know, in your basic calculus course, you learned, you know, to minimize certain functions, you would take its derivative and set that derivative equal to 0. That's sort of a basic calculus thing, right? In this case, we're going to generalize this to, that's unconstrained optimization. We're going to generalize this to constrained optimization, where we say not only is f convex, but also this x is restricted by these convex functions. So gi are a bunch of functions, m of them, for example, that are all convex, and there's these inequality constraints. These hj's, you can also have equality constraints, but this is a little more restricted. These have to be affine. So affine functions are these linear type functions, so like aj times x plus bj, right, for example, where this has to be an inner product between vectors, that this is equal to 0. So pretty much these hj's have to be linear, but these gi's can be convex. And this inequality being in this direction is very important. If you switch the direction of this inequality and this constraint, it would no longer be convex, right? Because then you could think about it as being negative gi being less than or equal to 0, and negative gi would be concave if gi was convex. So this basic form is just a basic form of convex optimization. So if I say that we have a convex optimization, you can assume that there exists some f, which is the convex objective, and some gi's, which are convex, which are these convex inequality constraints, and affine equality constraints. Okay. So the nice thing about convex functions is that local minima are global minima. This is sort of a dominating theme about convex optimization. And the basic idea is that all I have to do is say that, so let's define local minima really quickly. A local minimum is a point x0, such that if I just look within a row radius of x0, so I look at any x1 that's within row distance of x0, then that f at x0 is smaller than or equal to f at x1, right? So that's a local minima. Global minima doesn't have to be restricted to this row distance, this row radius around the minimum. So the reason why this is nice is that I only have to get local information about the function to validate that something is a minimum if this function is convex. Of course, convexity is an extremely strong assumption, which quite often we don't have or we don't want to have. But let's just stick with the convex case. And to imagine why this matters, you can think of a non-convex function, which if you had a minimum over here, this is the local minimum of the non-convex function, but that does not necessarily mean that this function is minimized at this point. We might go over here and it could dip below that that local minimum, right? So that's the obvious thing. And this function, this convex function, actually doesn't have a local minimum unless we extend the reals to include infinity, but because it's negative log t. Okay, so conditions of convexity. So these are things that have to hold if we are convex, and if we are convex, then they do hold. So under certain assumptions. So first of all, if f is differentiable, then we can compute a gradient. We can start talking about gradients of f. If it is differentiable, then this f of x is bounded below by f at x naught for any x naught in x, plus the gradient of f transpose x minus x naught. And the basic idea is that you have some tangent to the function, and the tangent bounds below the function everywhere. That's the picture that you have here. The second order condition is just saying if you're twice differentiable, then it's convex if, when we take any vector x, take its transpose times the Hessian. So Hessian is a matrix, right? It's a matrix of all partial second derivatives times x. So you form this quadratic form with x, then this has to be positive. So there's a lot of ways to talk about this. This means that all the eigenvalues of the Hessian exceed or are non-negative. They're at least 0. All the eigenvalues of this Hessian. That's one way to talk about this. This property that the Hessian, when you take this quadratic form, is non-negative. This property is called positive semi-definite. So I'll use that throughout. For any matrix, so I can put a matrix in here, and that's that matrix is positive semi-definite if and only if this holds, which is for every x, this quadratic form is greater than or equal to 0. And for this to work out, it has to be twice differentiable, and nothing about convexity forces it to be twice differentiable. You can have functions, and we'll talk about this, that are not even once differentiable. Right? And so, if you have differentiability, then this first order condition holds. If you have twice differentiability, then the second order condition holds, right? For convex functions. But convexity, again, is a pretty strong assumption. Okay, so some examples of convex functions are affine ones, quadratic ones for positive semi-definite A. So one obvious thing about this, one way to think about this is that if you think about this quadratic function, this A is the Hessian, right? So that's a hint for the next exercise. Right? And then the negative log function is convex as well for a real x. Log sum x is kind of an interesting one. Sorry, I'm not sure why this is showing up like this, but that's just the log of the sum over I of the exponential of these affine functions. So you have a bunch of affine functions, you take their exponential, you sum them up, and then you take the log. That's convex. Right? And there's a lot of operations that preserve convexity. So things like addition, partial minimization. So if you have a function in multiple dimensions and you minimize one of them, or some of them, those dimensions, and keep the other ones fixed, then what results, that resulting function is also convex. Composition of convex and non-decreasing convex functions. So this is very important. You have to have your convex function as non-decreasing for when you compose your convex function with that non-decreasing convex function for it to be convex. And very, very important, this comes up with neural nets, general composition of convex functions are not convex, and that's what a neural net is. An artificial neural net is the composition of multiple convex functions. Typically, we use convex activation functions with artificial neural nets. So only under very restrictive circumstances are compositions of convex functions also convex. Okay, so as an exercise, you should just go through these and show that they are convex. We're not actually going to go over this solution. They should all be convex. It's just a good exercise to verify this. And you can use any of those conditions. You know, all of these are smooth functions, so you could use any of the first or second order conditions, or just the basic definition of convexity in this case. So go through that exercise, and I'll meet you on the other side.